The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So these controlled low-strength material with recycled concrete fines, David Lange from the University of Illinois will be presenting. So Jacob is not here.
He's not here.
Oh, okay.
All right. Well, good afternoon, everyone. It's my pleasure to be here to share with you some of the results of our study on controlled low-strength materials with recycled concrete fines. Michael, this is a perfect presentation to follow yours, because both Michael's presentation and this presentation hit the basic theme of using a statistical experimental design when we're trying to explore mixed design and we don't know a priori exactly what the relationships are supposed to be. If you're just making traditional concrete materials, you can go back to Abrams' law and count on it to work and so forth. But when you're using recycled materials, you're facing probably the biggest challenge is that you don't really know exactly how these things are supposed to interplay. And that's why both Michael's presentation and our presentation are utilizing these kind of statistical experimental methods to explore the interactions. Okay, so let's go ahead and take a look at this. Oh, first of all, you'll note in the ACI program guide that the speaker was Jacob Henschen. Jacob received he's a graduate student in my group, and he received a teaching fellowship. So he's got different kind of duties right now that require him to be back at the plant, as it were. And so Jacob is not here, and so I'm, as his advisor, standing in for him. I'll see if I can do it justice. The work that I'm describing today is sponsored by O'Hare International Airport. We've been very pleased to have an 8-year-long running relationship with O'Hare, where they've been sponsoring our research through our Center of Excellence for Airport Technology. And O'Hare has been interested in green, sustainable strategies around the airport for quite a few years. Rosemary Andolino is the Commissioner of Aviation in the city of Chicago, and she's been key in promoting this idea of airports going green. So if you're in the aviation industry at all, you'll see these kinds of conferences and a new guide for the Sustainable Airport Manual I mentioned here that have been the work of O'Hare Modernization Program. The O'Hare Modernization Program has been going on for about 8 or so years, and it's an $8 billion infrastructure program. And the theme of it is to take O'Hare, which was built in the 50s with kind of a crisscrossing runway strategy that you see on the left map, and convert it into a more modern parallel design that you see on the right map. And the newer airports, Denver, Atlanta, and so forth, with the power and the weight of today's modern aircraft, we get better throughput if we're landing and taking off in parallel fashion rather than getting all the traffic interactions when we have crossways, runways. So there's a big incentive to think about recycling at O'Hare. And in a big program like this, there's a number of different concrete taxiways and slabs taken out of service. And they're stockpiled on a part of the airport, and they would be, the program would be forced to pay for their disposal in a landfill, and that drives one of the reasons that we want to see recycling of these materials. And we're working with the FAA to try to improve the rules that allow for recycled concrete aggregate, and the FAA is, of course, on our side. They're trying to help us make progress in this way. One of the things that we're trying to do with our recycled concrete fines is separate the problem into two parts. Recycled concrete is most often used to recover coarse aggregate. And that's basically the idea of the previous presentation, that we're using the coarse aggregate. But our focus here is that after you've successfully used all that coarse aggregate, you still have piles of fines that represent a really different kind of a challenge. Most often, people have given up on that. They're hard to use. The absorption characteristics are crazy and unpredictable. And so using it in normal concrete structural kind of materials has been problematic. The other reason that it's been problematic is because the nature of these fines is that they're very highly absorptive. I show a scanning electron micrograph on the lower image, and in that image you see the complexity of these particles, that they include little grains of the original sand, they include chips of the original aggregate, they have paste content, and it's very a complex particle. So that high variability limits its use, and usually what people will do is use these things as just a fill, maybe as a base for, roadways that are low criticality. We wanted to suggest something of higher value. And so controlled low-strength materials represents an opportunity for us to have higher value added to these kind of waste materials, the fines that come from the crushing operation. And we think that there's a lot of application for CLSM around the airport. And particularly, we think of this as the candidate of choice for backfill, flowable, self-compacting fill. And when you're trying to do this, oddly enough, the main objective is to get target strengths that are really pretty low. In fact, that's actually one of the hardest challenges, is to keep your strengths down around 300 psi. I'm not just missing a zero there, 300 psi. And the reason you want that is to make the material excavatable. And you see an interesting thing that's being done on the picture below is where they're using it for backfill around pipe and so forth. You can put in some color coding, as it were, and that way if your excavator hits something that's red, they know that I'm really close to the pipe and so forth, and they start using extra care and so on. So this kind of, the flowability of these materials is a great advantage for filling trenches and anything next to a foundation and so forth. So our goal here is to take this opportunity to use a recycled material, these fines, and create a mixed design methodology that will allow us to get to a useful, targeted performance efficiently. Our experimental goals, therefore, are to develop a universal mixed design method for CLSM, independent of materials. Of course, we're thinking about the fines, the recycled fines, but it could be any kind of fines. And compare the performance of what we're doing to if we were using sand or virgin fines. So there was a lot of experimental work done to get started on this, and we certainly looked at the literature to see what we could learn. And we early on came up with a strategic approach that looked at three basic kind of parameters that would guide us through this process. First of all, there was an observation that paste volume was very important for the flowability issues of these materials. The second parameter we chose to focus on was the water cementitious materials ratio. Certainly, we know from being concrete people that water cementitious ratio is thought to, does control strength. And then the third one is a ratio between the OPC, the cement added, versus cementitious materials, because we're using fly ash in these materials too. So there's this ratio that we can tune, and you can imagine where these kind of parameters are going to have most impact. So something like water cementitious materials certainly has some impact on strength, but something like flowability, the paste volume is going to be the strongest variable in that case. So we had these three basic target parameters, these ratios and so forth, that we were going to use. And we wanted to get an approach to think about how to go forward with an experimental program. So we contacted Michael and stole his diagram that he showed in the previous presentation. And so I agree with Michael's response that whether you call it statistical experimental design or design of experiments or response surface methodology. These are all a part of a family of techniques where we're using the statistical character and relationships of parameters to tune the relationships, thus give regression relationships that help us develop a empirical-based design approach. So this is called central composite design with 3 input parameters, and it will expose nonlinear and interaction relations. So in our case, we have the, let's see if I can help along with these pointer. We have these 3 particular parameters I just was mentioning, and we'll call them x1, x2, x3 right here. And then we have, that you see on the previous chart, you have the center point and all these different factorial points and axial points and so forth, giving us points that we're going to try to do experiments on the boundary of this cube so that we can build the regression relationships. And so we go ahead and execute that, first of all, as a cube, and then we apply values to it with the experimental values that we have. And then we're measuring kind of input properties like weight and pace volume and so forth that are part of that methodology. So basically what we wanted to do is through different kind of trial experiments and so forth, we started with a center point where the water cementitious ratio was 0.85. 0.85. That's really, really high, isn't it? So those of us who make structural concrete would recognize this very quickly as a low-strength material. The paced volume, 0.42. If you're making concrete, you would expect that number to be maybe 42%. You would expect that to be something around 30%. Here it's up at 40%. The OPC versus cementitious ratio, 15%. My goodness, that's really low. A lot of fly ash in there. So this is not concrete. This is really intended to be a very low strength, but still workable kind of material. Or not workable, but kind of not a segregating kind of material. So our properties of interest are a little different than what Michael talked about. He's talking about a material that can be used for paving. We're thinking about this backfill slurry kind of material. And so we're thinking about the slump flow and the subsidence, that would be the loss of volume over some time. And then, of course, we do keep an eye on compressive strength, but we're trying to target these low strengths. So there's a couple pictures of how we do that with cubes, cube in compressive strength, and subsidence is a volume change measurement, and then there's the slump flow picture. So our materials that we're using then are in the terms of aggregate. We have our sand and our recycled concrete fines that we're going to contrast in this experimental program. We're using a Class C fly ash, and we're using experimental design for a variety of combinations that are delineated down here at the bottom. So there's a number of things happening again and again in this particular program and so forth. We wanted to create a certain kind of comparability between our virgin sand and our recycled concrete fines. So we wanted to kind of make sure we had the gradation of these things compared, and felt that they were generally comparable, and so we would not focus much on the differences in gradation as explanations for differences of fluid properties. The CLSM testing, we certainly had we had this extended mixing time, so we wanted to make sure that what we were doing in the laboratory would account for the fact that these materials have to be very friendly in the field. The samples that were cast were stored at sort of normal curing conditions, room lab temperatures and humidity, 100% humidity until testing. The 100% humidity was important for the subsidence measurement so that we're not getting a drying shrinkage problem. And we use molds that could be split in, they're very fragile kind of samples, so the normal kind of concrete cylinder molds were not used, but we use these molds that were designed to come apart more easily. And the testing then was done at 14 days. So instead of demolding that you might do at 1 day for concrete, we did it at 14 days. There is there's some pictures of our slump flow, and you can kind of sense how this material is very fragile kind of material. Segregation, as a general rule, was not a big problem for these samples. We were pleased about that. That certainly is a big thing, that you don't want a big separation of your material when you're applying it. There's our slump flow. Subsidence was measured by measurement of these cylinders that were being prepared at 7 days. This one that you see there is a dramatic loss of volume. That's not the typical. You'll see later in the data that we're talking about subsidences of a percent to 3%. That's, I don't know what that is. That looks like about almost 10%. And compressive strength was done in kind of a conventional way, and also with cubes, but here we show the sun cylinders as well. Okay, experimental results. So with regard to the flow issues, one of the first things we were interested in is finding which of these parameters we were using tended to dominate the behavior. And the flow had its strongest dependence on paste volume. And most of these mixes that we were talking about are exceeding 8-inch flow, 200 millimeter flows, and that's a good thing. That's the kind of fluidity that we want for a backfilling kind of application. And of course, we identified some cases that we had this flash setting kind of problem, indicating that you certainly have to test your specific materials for their chemical compatibility. Subsidence, one of the findings there is that subsidence was most related to water cementitious ratios. And we can, one example had to do with the paste volume, for example, that these low subsidence values versus this curve being the virgin fine aggregate indicated how the difference between the two types of aggregate we were looking at was very substantial. In fact, we were seeing an advantage of the recycled fine aggregates versus the virgin fine aggregates in terms of subsidence. And we think that that has to do a little bit with the angularity of these particles. They're certainly more angular than the virgin fine aggregate particles, and therefore their ability to resist some of this settlement subsidence phenomenon that happens in this class of materials was improved versus the virgin fine aggregate. Compressive strength, as you might imagine, that was dependent on the water cementitious ratio. But unlike, often in concrete we think about Abrams' law, the water cement ratio law, as just basically governing the relationship between compressive strength and the mix design. But this OPC cementitious ratio certainly plays a part in there as well in the case of the class of materials that we're dealing with. So part of the conclusion of this set, as I guess we anticipated and we hoped for, and one reason we were using experimental or statistical design was that we anticipated that there was an interaction between these three primary variables we were studying, and that one of them by itself would not be sufficient to characterize a mixed design's performance. So for example, here it says water cement ratio, OPC versus over cementitious ratio cannot predict compressive strength alone. And therefore, we need the partnership of these three parameters together to really predict our behavior. Another main focus was to get a handle on the comparison of our two aggregate sources. And we were pleased that we found arguably benefits from using the recycled fine aggregate versus the virgin fine aggregate. Insofar as we saw greater flow, less subsidence, lower strengths when using these recycled fine aggregates, all things that work in our favor for this class of material. So for the summary of this part, we have the flow was found to be primarily related to paste volume. Subsidence is a function of water cement ratio primarily. Strength was strongly controlled by cement content and water cementitious ratio. And overall, the recycled fine aggregate worked very well and perhaps favorably compared to virgin aggregate for CLSM. Okay, so this all was a great ending of this project and led us to go to O'Hare with the results. And O'Hare basically said, put it into a package for us so that we could utilize these kind of CLSM materials in the field very quickly. What would be your basic recommendations? So we wanted to boil down these recommendations into something very practical that could help people execute CLSM right away. And this is what we came up with. Number one, we addressed some of the initial testing of the materials strongly, so that they realize it's really important to characterize the specific gravity absorption of your particles, the bulk density gets your void content, and so forth. And these kind of standardized tests help you get those kind of parameters. And then there's a test for setting behavior if the set time happens to be important. Then we said, go ahead and do a calculation of the percent voids that you have in your aggregate system. Multiply that times 1.1, the voids that would be present between your aggregates, and that can be used as a starting point for your paste volume. Okay? And if you have that, okay, so that would be the first thing to tune this initial center point that you're going to try to hit and get good workable materials. The second recommendation is start with a water cementitious ratio of 0.7 and start with an OPC versus cementitious material ratio of 0.18. So make up this material and do some of your testing on subsidence and strength development and flow. And then we have these corrections to suggest. To get flow to be greater by 1 inch flow, increase your paste content by 1.4%. If your subsidence is not satisfactory, you can decrease subsidence by decreasing either your OPC versus cementitious ratio or by decreasing your water cementitious ratio by these kind of increments. Lastly, if compressive strength is not quite high enough for what you're trying to go for, you can increase your compressive strength by increasing your OPC versus cementitious ratio and by these increments, and we have sort of a recommendation with the relationship with how many PSI of increase it may give you. So as you can see, it's a very kind of a practical approach, but on materials like this that are not structural, this we found to be, our partners at our host certainly found this was the right tone to what kind of recommendation they were looking for. So the last thing I want to do is certainly acknowledge our sponsor, and with that, I'd be happy to take any questions that you might have.